Hi there, this is a little slideshow on learning about the types of chemical bonds. If you're watching this in class, you should have access to a folder full of a few different sheets to look at to practice. Otherwise, when I prompt you, just pause the video so that you can practice on the screen. So just a little review. Valence electrons we've been talking about are the outermost electrons that atoms have. Take a moment to look at this shortened periodic table to observe the pattern that you see for the number of valence electrons in each group of elements. You should notice that those elements in group 1 have 1 valence electron, group 2 have 2, 3 have 3, and then you'll see 4 is truly 14 is they have 4, and 5 has 5, and so on. The exception is group 8, helium has 2. Instead of following the octet rule, it follows the duet rule. Since it has just one shell, it can only hold 2 electrons. So again, valence electrons are those electrons in the outermost shell of an atom, and those can be shared with or transferred to other atoms. And every group or column of atoms in the periodic table, remember we're excluding the transition metals for now, we'll talk a little bit more about them later, they have the same number of valence electrons, which is why they've been grouped in that way. Noble gases have a full electron shell, and that makes them very stable. And one more review, we're going to focus in on electronegativity, which again is the tendency of an atom to attract electrons to itself. I like to think of it as an ability of an atom to steal electrons from other atoms for itself. The trend, excluding the noble gases who do not have an electronegativity value, or in fact it's 0, it increases as we move to the right and up the periodic table. Do you remember why noble gases have an electronegativity of 0? Think about whether or not they want electrons at all. So if you have your packet, find model 1. It looks just like this. If not, no worries. We're going to take a look at this. So taking what we just learned on the previous slide or two, right above each of these lines, how many valence electrons each of these groups has. Notice we have removed the transition metals. So either pause the video and do it now on your sleeve, the plastic sleeve, or pause the video and just practice on your screen. So hopefully you came up with these values that you see here, 1, 2, 3, 4, 5, 6, and 7. We don't have the noble gases on this slide. So what's the relationship between electronegativity and the valence electrons? Try to observe a pattern in the periodic table that you're provided here and the number of valence electrons. And then think, why do you have this relationship, or why do we see this relationship? Please talk with your elbow partner if you're in class. And notice these are not masses, these are electronegativities. So again, pause and discuss before you move to the next slide. So there's a connection between valence electrons and the electronegativity. In general, the more valence electrons that an atom has, the higher its electronegativity. This has to do with the fact that the atoms that have more valence electrons are closer to completing their octet or duet rule and being stable like the noble gases. So moving on, find your next model if you're in class and find this plastic sleeve, or just look at the screen. What you're looking at here are 3 models that represent types of bonds. In the gray area that you see, that's where electron orbitals would be. In other words, the gray shaded area is where electrons are traveling. The 2 dots that you see would represent the nuclei of atoms. When 2 atoms bond, there are 3 possible scenarios. 1, neither atom will attract the electron strongly and the electrons are able to move freely. Number 2, both atoms attract the electron strongly and the electron is held between the atoms in kind of like a tug of war. They're fighting over it. Number 3, one atom attracts the electron more strongly than the other and ends up pulling that electron toward itself. With that information, try to, on your plastic sleeve, label A, B, and C with the correct number 1, 2, or 3, or practice on your screen to figure out which of these descriptions matches the images you're looking for. Pause the video now to do so. Hopefully this is what you came up with. If you look at model A, both of the nuclei have electrons around them, and the electron cloud has been kind of squashed as if they're pulling on them and stretching the electrons between them. So that matches up with description 2. Looking down at picture C, you can see the two darkened nuclei, and only one of them has any electrons around it because it stole it from the other one. And so that matches up with number 3. Lastly, in B, you see the two nuclei and the really large electron cloud or orbital where no one seems to be pulling or caring what's happening with the electron. And so there is sharing, but truly it's very loosely done so. So that matches up with description 1. Okay, let's move on. Now let's use model 1, which is our electronegativities for selected elements, and model 2. You'll see that I've given you 3 different pairings. Number 1 is fluorine and fluorine, 2, lithium and oxygen, 3, lithium with potassium. So using what you can see on the electronegativities, try to match up these 3 bonding pairings with the correct models that you see in the pictures. So you would write a number 1 next to A, B, or C, 2, and 3 in the same way. Pause the video and do that now. Hopefully this is what you came up with. So A would pair up with number 1. Here's why this makes sense. Two fluorine atoms will have the same electronegativity values, so they're going to both be pulling hard for that electron and trying to steal it from one another. If you look at model B, that again is that loose sharing of electrons. That matches up with lithium and potassium. Lithium has an electronegativity value of 1. Potassium has an electronegativity value of 0.8. Comparing with the rest of the electronegativity values you see on the table, those are very low. And you almost might think that, gosh, these guys don't really care what happens with their electrons. So that gives it that spherical shape. And then lastly, C, you can tell that one atom basically took the electron away from the other one. So if we compare lithium and oxygen, again, lithium has an electronegativity value of just 1, whereas oxygen has a very high electronegativity value of 3.5. So it has a tendency of stealing electrons from those atoms that have low electronegativity values. And so that's why model C matches up with that particular bond between lithium and oxygen. Okay, now we're going to start to apply these ideas to 3 specific types of bonds. And toward the end, you'll have an opportunity to write down all that you need to about each bond. So for now, I'd like you to just focus on the tasks. In metallic bonds, neither atom has a strong attraction to the electron. So neither one really cares what's happening with its electron. Which of our 3 scenarios in model 2 is a metallic bond? A, B, or C? Pause the video, discuss with your partner, and jot that down. Hopefully you came up with B. Again, that spherical pattern of the electron is just kind of a loose attraction to the electron, so it's just going to be orbiting around both nuclei. Here we're looking at a periodic table. Remember, neither atom in a metallic bond has a strong attraction to the electron. Either on the screen or just in discussing by looking at the periodic table or looking at your own periodic table, which elements would we likely see to form metallic bonds? Either sketch it on your screen or just discuss. Hopefully this is what you came up with. Remember, all the elements to the left of the stair-step line are metals. That does not include hydrogen. So this is going to form between atoms with low electronegativity values. In other words, metallic bonds form between 2 metals. Probably not surprising. Okay, moving on. Covalent bonds. Covalent bonds involve atoms that both have a strong attraction to the electron. So they share the electron. So these are going to have high electronegativity values. And they'll share them, but don't be fooled. They're not sharing them nicely. They're just tugging against them and nobody wins necessarily. So given that, which of these models, A, B, or C, best fits the description of a covalent bond? Pause the video as you discuss and label on your plastic sleeve. Hopefully you came up with A, Again, we get that squashed orbital where the electron is just being tugged and squeezed between two different nuclei. Looking at the periodic table then, again, covalent bonds involve atoms that have strong attractions to their electrons, so they share the electron. Outline the areas of the periodic table below where you think the elements are likely to form covalent bonds. Pause the video as you discuss. And hopefully you came up with what you see on the screen outlined in this teal color. So this is going to involve hydrogen and the elements to the right of the stair-step line, excluding the noble gases. Remember, they are inert, which means they do not react. So these form between atoms with high electronegativity, and in other words, covalent bonds are between two nonmetals. And then lastly, we have ionic bonds. Remember, ions are charged particles, so they have an excess of electrons or not enough electrons to match up with the number of protons. So in an ionic bond, one element attracts the electron more than the other, so it steals the electron, forming an ion. So which of our last three models here would match up with an ionic bond? Pause the video and discuss with your partner as to why you came up with that answer. And I'm sure you deduced that it had to be the last model, but make sure you understand why that one atom is left without the electron, whereas the atom to the right stole the electron, and that's why we see that orbital around it. In ionic bonds, again, one element attracts the electron more than the other, so it's stealing that electron to form an ion. Given what we've learned so far, now try to decide what areas of the periodic table would involve elements forming ionic bonds. Pause the video as you discuss. So notice here we've got two colors going on. Ionic bonds need to include an atom with low electronegativity, so that would be our metals, and a second atom with a high electronegativity, that would be our nonmetals. So we see that ionic bonds form between metals and nonmetals, so one of each to form these compounds. So here are the key ideas that you're going to want to take some time to write down. So in metallic bonds, again, neither atom has a strong attraction to the electron, so the electrons move freely in kind of like a sea of electrons. And these form between two metals. They both have low electronegativity, and that's why you see this sphere on the right. And you might remember that metals conduct electricity very well, and this has to do with the fact that their electrons can move freely. In covalent bonds, both atoms have a strong attraction to the electron, so they share the electron tightly. And these are going to form between two nonmetals, both having high electronegativity values. And then lastly, in an ionic bond, one element will attract the electron more than the other, so it steals the electron, forming an ion. Ionic bonds form between a metal and a nonmetal, where the metal has the low electronegativity and the nonmetal has the high electronegativity. In your notes, make sure you get all these ideas down, and I would also make sure you include the diagrams. You'll be expected to be familiar with those and maybe even have to recreate them. So pause here as you write these ideas down. We've got just a couple more ideas left to cover. Before we get to some of the exceptions for the three types of bonds, let's practice a little bit first. We've got 4 to practice on. Feel free to write these down or discuss with your partner. We'll go through all 4 and then you'll see the answers. So using what you've learned, predict what kind of bond would be found in O2. Take a look at your electronegativities if you like. I think that would be helpful, and see which kind of a bond this would be. Pause the video as you discuss. Number 2. Here is another substance, potassium chloride, so that's KCl, potassium and a chlorine. What kind of a bond would this be? Look at your periodic table to figure that out. Pause the video as you do. Number 3, you're looking here at methane, CH4, so a carbon and 4 hydrogens. Figure out what kind of a bond this would be. Be able to provide reasoning. And your last example is iron, just Fe. If you had a whole lot of iron, what kind of a bond would you expect there? All right, let's see the answers. Hopefully for number 1 with O2, you came up with covalent. 2 of the same type of non-metal would be a covalent bond. Potassium chloride is an ionic. The potassium is a metal, the chlorine is a non-metal, so the chlorine would take electrons from potassium. Carbon and hydrogen are both non-metals, so that would make it a covalent. They would be sharing their electrons. And then just a bunch of iron is going to give you a metallic bond, and again, that's just a really weak bond. So we've got just a little bit left here. Now, not all bonds fall in one of those 3 categories, so let's make sure you write these things down. We have what are called in-between bonds, because not all atoms have very high or very low electronegativity, and so they don't necessarily fit neatly in the 3 types that we see in those in-between bonds. So for example, when you're looking at this triangle over here, you see ionic at the top, covalent at the bottom right, and metallic on the bottom left, with different elements and compounds along the bottom and the right side, and then of course some compounds in the middle. And so where it's kind of bluish purple are all the metallic bonds, reddish is ionic, and down in the yellow corner is covalent. But then you've got these kind of in-between areas where the electronegativities are kind of average. We have something called polar covalent and semi-metallic. So let's take a look at the next slide to look at what this actually means. So polar covalent bonds, and again, I would write these down. You would probably see some of this material on the non-ELO part of your test. Electrons are shared unequally between 2 nonmetals. They spend more time around the more electronegative atom, but still spend some time around the less electronegative atom. This is an in-between an ionic and covalent bond, but we would call them polar covalent. It tends to create oppositely charged poles in the molecule, and I'll show you that in a picture here in a second. So a good example is water, H2O, where, and I'll talk about those images on the right in a moment. So oxygen has a higher electronegativity value of 3.44 compared to the 2.2 of the hydrogen. So even though it's covalent, the electrons are pulled more tightly toward the oxygen, and they hang out around the oxygen more often. This causes that part of the molecule to have a negative charge, and then the hydrogen ends to have a positive charge, and that's where we get this idea of them being polar, because they have 2 poles. Now take a look carefully at this electronegativity value. Non-polar covalent bonds have a difference between the 2 atoms in electronegativity between 0 and 0.4. So if the difference is within that range, it would be nonpolar and the electrons would be shared equally. However, when we get to the polar, it's a pretty wide range, but if the electronegativity is greater than 0.4 and less than 2, it's polar. And so the more electronegative atom will pull those electrons closer to it, giving this end a negative charge, and the opposite side would have a positive charge. Once you kind of go over that boundary, if you will, of 2.0 and the difference in the electronegativity values, then this atom just plain old steals the electron and it becomes an ionic bond. So it's kind of an interesting look at how electronegativity can determine what kind of bond we get. And then lastly, about water, you've probably poured a glass of water too full before, and it almost created like a water bubble at the top of your glass, but it didn't spill. And that has to do with this polarity, where these oppositely charged poles will be attracted to another opposite water molecule. So this oxygen would be attracted to a hydrogen end of a water molecule somewhere else, and it creates this lattice where water is attracted to water. And this is why it's really difficult for you to, you can spill a glass of water, but you can kind of overfill your glass and kind of pull it off, and you look pretty fancy, but it's just water being cohesive. All right, and then lastly, our semi-metallic bonds. Here, electrons are less free to move than in a metallic bond, but freer than we would see in a covalent bond. And these in-between metallic bonds, they're in between a metallic bond and a covalent bond, And this might not be too surprising, but this happens between metalloids. So remember, those are the elements that border between metals and nonmetals. So remember, they're semiconductors, but that's not as quick as a metal. And so it makes it good for not overheating in our computer chips, etc. And again, we've called these guys semiconductors, for example, silicon. And that is it, and I hope that was helpful.